Now we'll in this class we will start with another novel separation process that is quite important and gaining much importance in nowadays, and this is supercritical fluid extraction, and this is the last topic of our course. Now, this is an emerging separation process, and to understand the basic principles of supercritical fluid extraction, we have to just look into what is called critical condition. Critical condition is a condition, a set of certain temperature and pressure condition. It is a set of temperature and pressure condition where you cannot distinguish between the liquid phase and the vapor phase of a particular substance, where liquid and vapor phase of a substance becomes indistinguishable. Okay. So, at that particular and any the substance beyond that critical condition is known as the supercritical fluid. Okay. The substance beyond the critical condition beyond critical points is known as the supercritical fluid. Now, I will just give a schematic, a schematic of a typical pressure temperature history of a substance. Is the pressure, is temperature, this is the solid phase, and then you can have a liquid phase, and beyond this critical condition you will be having the supercritical regime. So, here you have a vapor phase and you have a solid phase here, you will be having a liquid phase there, and this is the critical condition, and you cannot distinguish between the liquid and vapor phase beyond in the supercritical regime. Okay. The physical and the thermal properties have some of the changes of these properties are very important in the supercritical fluid regime. So, I will write SCF in supercritical fluid regime. The thermal and physical properties they undergo a remarkable change. What are these changes? Number one, they possess the liquid like densities. They possess the liquid like densities. There is a tremendous reduction in surface tension. Surface tension, you can have a gas like viscosity. The viscosity will be extremely small, extremely low, gas like viscosity. So, you will be having a liquid like density. So, density will be higher, but you will be at the same time you will be having a gas like viscosity. The viscosity of a gas is typically 2 order of magnitude less than the viscosity of the liquid. Okay. The surface tension is reduced tremendously. You can have the compressibility like a gas. And diffusivities are becoming quite large and they becomes higher than the liquids. So, these properties become very important and they play a crucial role in the extraction of the solutes in a supercritical fluid. Okay. Now, let us look into some of the commonly used supercritical solvents. The commonly used supercritical solvents, first one is carbon dioxide, nitrous oxide, ethylene, propylene, propane, N-heptane, ethanol, ammonia. These are some of the commonly used supercritical solvents. Among them, the most widely used and the popular is carbon dioxide. Now, let us look into some of the critical conditions of these fluids. The substance, that means the compound that we are talking about, critical temperature in degree Kelvin, critical pressure in atmosphere, and let us say density in gram per cc. Carbon dioxide, its critical temperature is around 31 degrees centigrade, okay, 304 Kelvin. Okay. The critical pressure is tremendous, it is 73 atmosphere and its density is 0.47. Okay. Ethane has a critical temperature in the same range around 35.5 degree Kelvin, but it has a lower critical pressure 48.2 atmosphere and its density is further lower. You have ethanol. In ethanol, the critical temperature is 516.6, this is 63 atmosphere and the value of density is around 0.28, and propane has a critical temperature 370 Kelvin, its critical pressure is quite low 42 and its density is 0.22. Okay. Now, so these are the various substances used for the supercritical fluids. Now, we will be looking into some of the properties of these supercritical fluids that made them so superior compared to the other species. Okay. So, the first question we are going to answer is why carbon dioxide is a supercritical fluid. Okay. Now, I am just listing some of the properties that qualify carbon dioxide as a good candidate for a supercritical fluid because of following properties. What are these properties? Just listed some of the properties. Low critical pressure, it is only 74 atmosphere, low critical pressure, and temperature. Secondly, carbon dioxide is relatively non-toxic. CO2 is relatively non-toxic. This is very important property. It is inflammable, it is not flammable. Fourth one is this is available at high purity. Generally, the carbon dioxide is available more or less at relatively high purity, available at purer form. The cost is low. This can easily be removed from the extract. That is an important property, because if the solvent is there in the extract, then that becomes a contaminant. So, how easily or how quickly you can remove the solvent from the product, that becomes an important property. So, carbon dioxide can be removed quite easily from extract. It has polarity like liquid pentane and this is it contains, it has polarity like liquid pentane at supercritical condition therefore, is best suited for the lyophilic compounds. So, so these are the various advantages of advantageous properties that carbon dioxide possesses to be a supercritical fluid, but the main drawback or disadvantage of carbon dioxide is it cannot extract the polar solute. Okay. Then we will see some couple of more supercritical fluid. Next supercritical fluid is nitrous oxide. Nitrous oxide, the main advantage is it is good for removal of polar solutes. Why it is good in this particular aspect? Because it has permanent dipole moment, as it has permanent dipole moment. A typical example of nitrous oxide is that nitrous oxide is better than CO2 for extraction of polychlorinated dibenzoxidines from fly ash. Okay. So, this is called PCB. Okay. These are very carcinogenic, highly carcinogenic, but main disadvantage of using nitrous oxide is that it has relatively high critical conditions, high pressure, high critical pressure, high PC and Tc. It means Tc is greater than 374 degrees centigrade and Pc is greater than 221 bar. So, it has high critical pressure and critical temperature, and this basically nitrous oxide becomes very explosive. Okay. Sorry, at critical condition it becomes explosive. That is the main disadvantage. At critical condition, it is explosive. The next material that we will be looking for is, we will be discussing about H2O, the water. The main disadvantage of water, for using of water as supercritical fluid, as it has a very high critical conditions, high critical pressure and temperature. Critical pressure is more than 220 bar, that means 220 atmosphere, and Tc is greater than 374 degree Kelvin. Okay. Now, at these conditions, the point is, at these conditions the water becomes corrosive. Okay. Now, let us look into the, so these are the some commonly used supercritical fluid, and we just chalked down noted some of the advantages and disadvantages of this various solvents, and depending on a system we have to select a particular solvent to for the extraction purposes, and most commonly extractant that is used is carbon dioxide. Now, let us look into some of the important properties, important parameters for supercritical fluid extraction process. Number 1 is threshold pressure. What is the threshold pressure? This is the pressure where the at normal pressure and temperature condition, there will be the miscibility of the solute and the solvent gas will be 0, almost there is no miscibility. If you go on increasing the pressure at beyond a particular pressure, beyond a critical pressure onwards, the solutes becomes soluble, it becomes miscible, that means its solubility increases in the solvent. The particular pressure where the solubility just becomes some value apart from 0, that particular pressure is known as the threshold pressure. So, if you plot the solubility curve, let us say in gram per liter and versus pressure, then beyond a particular pressure the solubility starts. This is the solubility curve for at 45 degrees centigrade for carbon dioxide. This particular pressure is called the threshold pressure. This threshold value basically indicates the minimum pressure at which solute becomes miscible. Okay. Second one is the pressure at which the maximum solubility you will be getting. That is a very important parameter. Pressure at which solute reaches its maximum solubility. Okay. This is very important parameter. That means, if you can identify the pressure where the solubility is maximum, you need not to go for higher pressures. Okay. So, that gives a limit on the operating condition that you are operating the system. The third important parameter that you are going to see is the knowledge of physical properties of solutes. Okay. The solutes are better are dissolved better if they are in the liquid state compared to the solid state. So, this knowledge of the physical state of the solute, for example, the physical property, the important physical property you are talking about is the melting point. Solutes are solubilized, solutes are dissolved better in liquid state compared to the solid state. So, this knowledge of the physical property of solutes are very important. Sometimes one uses the co-solvents or modifiers. What are the co-solvents? These are known as the co-solvents or modifiers. What is their role, their purpose? The purpose is to modify the property of the solvent. The co-solvents are added to a small extent in order to modify the property of the solvent. For example, what is the modification of the property? The modification of the property may be modification of polarity of solvent, so that the solubilization capability of the solvent will be more. Okay. So, it can solubilize the polar solvents as well. Okay. So, that the solvent can solubilize polar solvents as well. Okay. We can give an example. 1 to 10% methanol is added to CO2 in order to increase its polarity. Okay. The polarity of the carbon dioxide will be increased if you use some co-solvents or modifier present in the system, so that the its solubilization capability will be increasing. Okay. Now, let us now jot down some of the advantages of supercritical fluid extraction process. The first advantage is that the simple expansion of supercritical fluids leads to lowering in solubilization capability. That means, beyond critical point, my solvent has greater affinity to dissolve the solute. Okay. Solvent has better or higher capacity to dissolve the solute. On the other hand, if you expand it, expansion means you are reducing the pressure. Okay. On expansion, that means on expansion means on reduction of pressure, reducing the pressure, the solubilization, the solubility of the solutes becomes less. This lowers the solubility capacity. Because of this property, the solutes can easily be separated from the supercritical fluid. Solutes and solvent can be separated easily. Okay. The second advantage that you will be getting is that they have these supercritical fluids, they have the liquid like density, but higher diffusivity compared to liquids, with respect to liquids. They have the lower surface tension, because of these two properties their mass transfer resistance becomes, mass transfer behavior is much superior when you are talking about the penetration of the solvent into the solid matrix to dissolve more solvents those are present inside the solid matrix. So, since the surface tension is very small and the diffusivity of the solvent will be pretty high. So, they can penetrate easily the solid matrix and dissolve solutes. That means, if you have a material where the solutes are present on the surface as well as inside the material, okay, because of these properties of the supercritical fluid, lower surface tension and higher diffusivity, they can penetrate from the surface inside the material, can attack the solutes and can dissolve them and can take them out. Okay. So, these are the two important advantages of any supercritical fluid extraction. Now, let us look into the mechanism of solubilization of the solutes from the solid materials. Okay. There exists 4 mechanisms. What are these? Number 1, if there is no interaction between the solute and the solid phase, if no interaction between solute and solid phase, the process is known as the dissolution of solute. Okay. It is the mechanism is dissolution of solute in supercritical fluid solvent. Okay. Now, if there is an interaction between the solid and the solute, and solid is present, then the mechanism is desorption. it is just a reverse of adsorption. Okay. So, in an adsorption column what is done, basically in the solid phase the solute gets attached to the solid phase. Okay. And this attachment is by van der Waals forces, physical adsorption, chemical adsorption, so on and so forth. On the other hand, if you like to remove those solids present in the solid phase or the adsorbent phase, you have to run a liquid. Okay. And by the desorption, these solutes will be coming out from the solid phase or the adsorbent phase, and this desorption will be dictated by the desorption equilibrium. Similarly, in the case where there is an interaction between the solutes and solid matrix is present, that means interaction means the solutes are attached to the solid matrix, but by weak van der Waals forces or chemical forces. Okay. Now, if you add the supercritical fluid, now these solutes will be coming out of the solid matrix, and the mechanism is exactly like desorption. Okay. And desorption will be basically dictated by the equilibrium isotherm. It will be dictated by desorption equilibrium isotherm. Then third mechanism, one can have swelling of solid phase by solvent occurs. Okay. The solid phase takes up some amount of solvent and it swells, and then extraction of entrapped solutes through the first two mechanism. Once the solid phase gets swelled, then extraction of solute occurs by either dissolution or desorption. If there is no interaction of the solute and the solid matrix, then the mechanism is dissolution. In another case, there is interaction, it will be by desorption. Okay. The fourth one is reactive extraction. In this case, the insoluble solutes react with the solvent and products are soluble, and hence the extractable. Okay. So, solutes which is basically insoluble in supercritical fluid, they react with supercritical fluid, okay, and this product becomes soluble. So, therefore, the product comes to the supercritical fluid, not the reactant. So, once it comes to supercritical fluid, it can be extracted. Okay. This leads to a feasible extraction process. Okay. The example of lignin extraction from cellulose is one example of reactive extraction. Is an example of reactive extraction. Okay. Then let us look into the thermodynamic properties. Since we are talking about the critical conditions, adsorption, desorption, so it must be very clear now that some of the thermodynamic properties are becomes very important in case of supercritical fluid extraction. So, temperature, pressure, equation of state, adsorption equilibrium constant, solute solubility, these are very important thermodynamic properties which are quite relevant in supercritical fluid extraction. Now, let us look into some of the basic and simplest form of the supercritical fluid extraction technology. Basic SCF technology. This is known as RESS, RESS. This is rapid expansion of supercritical solution. So, in this case the supercritical solvent takes up the supercritical beyond the critical conditions, the fluid becomes, the solvent becomes supercritical. The supercritical fluid becomes more powerful in order to solubilize the solutes. Once it will solubilize the solute, it will be expanded rapidly. So, what is the essence? Because of that its solubility decreases significantly. So, the solutes that has been solubilized by it will be separated and you will just recover the solvent and the extraction will take place. Okay. So, a basic typical flow sheet we can draw of this process is something like this. You have a fluid reservoir, then it goes through a preheater, because you have to heat it up to raise its temperature. Then there must be a pump, okay, pressure regulator, goes to the material, the solute and solid matrix where the solute has to be removed. After once, so the supercritical fluid dissolves the solute present here, then it is expanded through this valve. There may be a heating region, heater, and it will be, after heating it may be expanded, and this is an expansion nozzle. And there may be a collector here, okay, and this is the collector surface. After expansion it becomes, the solute becomes less soluble and they will be collected, and this is basically nothing but a collection chamber. This is the collection surface and this is the collection chamber. Okay. So, this is the typical flow sheet of a RESS process, and let us look into some of the salient features of this process. We have the supercritical fluid to be pumped through the preheater. Heater. Where it has to be pumped? It has to be pumped into a vessel containing solid solute, okay, and the solution is then sent to the precipitation chamber by expansion through a capillary or laser drilled nozzle. Okay. Then the dissolution takes place. Dissolution of solute in the supercritical fluid takes place. Okay. Then it moves to a precipitation chamber by expansion through capillary or laser drilled nozzle. Okay. And what happens in the precipitation chamber, and through this laser drill nozzle it is expanded, that means the pressure is released. Since the pressure is released, its velocity is very high. The velocity of the solvent may be supersonic, velocity may be supersonic. Okay. So, you are just releasing pressure from the high pressure, you are just releasing at the atmosphere, or it is a low pressure. So, it will be coming out at a great velocity. Okay. And let us see what happens in the precipitation chamber. In the precipitation chamber, pressure is much lower. Okay. And at that lower pressure, the solubility of the solute becomes quite low. Solute solubility is low in supercritical fluid. So, therefore, the solute comes out of the solution, that means it precipitates. So, this leads to precipitation of solutes. Now, so so basically it will be separated out, and size distribution and morphology of the precipitated material is basically a function of the its concentration, various conditions. Morphology is a function of pre-expansion concentration and its condition. And pre-expansion concentration depends on several factors. Depends on number 1, the supercritical fluid. Suppose a particular solute is more soluble in a particular supercritical fluid, maybe in carbon dioxide. If you use nitrous oxide, then the concentration of solute will be low because the solubility is less. So, it depends on the concentration nature of the supercritical fluid that you are going to use. Secondly, of course, the nature of the solutes. If you are using carbon dioxide as supercritical fluid and you are using a polar solute to dissolve, the dissolution or the solubilization will be less. Okay. So, nature of the solute will also a factor. Then addition of the co-solvent. Or modifier. Now, if you are using carbon dioxide and if you are using if you would like to extract a polar solute, then if you add a co-solvent, then that will increase its polarity and its solubilization capacity of the polar solutes. So, the addition of co-solvent is also very important factor, and of course, the operating temperature and pressure. Now, generally it is found that particle size of precipitate is smaller and distribution is narrower if pre-expansion concentration is higher. Okay. Now we will just take a particular example. The particular example that we will be talking about is that example of naphthalene extraction. The process, a typical naphthalene extractor looks something like this. You will be having the extraction vessel. In this extraction vessel, the supercritical fluid is mixed up with naphthalene, and naphthalene is dissolved in the supercritical fluid. Okay. Then it is going through a pressure reduction valve. So, expansion. Okay. So, once it goes through a pressure reduction valve, what happens? The solubility of the naphthalene, which was very high in the supercritical fluid at that those operating conditions, it becomes certainly low. So, it goes to a separator. Here you separate out the naphthalene. Okay. Is separated out, and the supercritical fluid, what is it should not be wasted, it will be compressed and it will be, its pressure will be increased and it will be sent back into the extraction chamber. So, supercritical fluid comes here via a compressor, and it is sent back to the extraction vessel, so that the whole system becomes a continuous process. Okay. Now, in the I will draw a solubility diagram of typical naphthalene under a supercritical condition. In CO2. Okay. This is the concentration of naphthalene, that is weight percent. This is a log scale. Okay. And this side is temperature, degree centigrade. Typically the plots look something like this. The solubility curves becomes very high at 300 bar and at this temperature. Okay. This 120 bar, this is 90 bar, this is 70 bar. Okay. And this temperature is 20 here, 30 there. Okay. It is around 40 here. So, it is around 65 there, and this value is around 15, and this will be here at 1. Okay. The solubility is 1% here, but the solubility shoots up to 15% when here the solubility is 15% when you are operating at 65 degree centigrade, and it is around 55 degree centigrade, 55 degree centigrade and 300 bar. Okay. So, no, this is around 70 degree centigrade. Okay. So, when you are going for high pressure like 300 bar and high temperature 70 degree centigrade, the concentration of naphthalene becomes very high. So, it dissolves into a large extent in the carbon dioxide. Now, the naphthalene chalk dust mixture is fed to the extraction vessel. And the condition is, let us say 300 bar and 55 degree centigrade. Now, at this condition the carbon dioxide contains dissolved naphthalene, that is around 15 weight%. Then it expanded to 90 bar through a pressure reduction valve, and after that the temperature becomes 36 degree centigrade. Now, at this condition, at this pressure and at this temperature, the solubility of naphthalene is only 2.5%. Okay. So, rest of the naphthalene falls out of the solution. So, rest naphthalene comes out of the solution. Okay. The precipitated naphthalene is then collected and the supercritical carbon dioxide is then compressed to 300 bar, and at 55 degree centigrade its temperature is risen to 55 degree centigrade, and it will be sent back and recycled to the extractor. Okay. So, that is the total typical procedure. Now, I will just mention some of the special application of supercritical fluid extraction. Removal of fat from foods, extraction of vitamin E from natural resources, removal of alcohol from wine and beer, fourth one is removal of pesticide, and finally, you can extract polyaromatic hydrocarbons which are carcinogenic in nature, and in short they are called PAH, polyaromatic hydrocarbons, and polychlorobenzene PCB, and all these are carcinogenic organic solutes. They can be removed by using supercritical fluid extraction. So, in this separation process we have seen the quality of the supercritical fluid, and we have looked into the various solvents, what are the advantages and disadvantages of these solvents, and the basic principle of how they will be operating, the thermodynamics, the increased solubility beyond the critical points of the solutes becomes very important, and when you reduce the pressure, when you reduce the pressure and the solubility of the solute in the supercritical fluid falls drastically, therefore, the dissolved solute will be precipitated out, and one can take out the supercritical fluid and further compress it and send it back to the extractor. In fact, one can look into the molar chart and do some thermodynamic calculations and can find out what will be the amount that will be extracted per unit mass, per kg or per pound of the supercritical fluid, and what are the relevant energies associated with it. Okay. So, with this we come to the we finish the supercritical fluid extraction process, and basically this is the last chapter of our course. And if you remember that we have, if you look back, you can see that we have talked out about various novel separation process ranging from membrane based separation processes in detail, and the chromatographic processes, the supercritical fluid extraction, centrifugal processes, ion exchanges, and electrophoretic separation processes, so on and so forth. Okay. Thank you very much.